We'll get started at 35. Sorry? Anna? She's still an officer. If that, yeah. Yeah, so she was the president until December. SIG is kind of weird because one of our presidents graduated early. So the whole election cycle got shifted a semester. So instead of it being every spring, it's every December. Yeah. So I'm the current president, and then Arif is the VP.
It's actually fun though. It's no.
Cool, I think we can get started. So, hi everyone, I'm Jacob. I'm the president of SIG. Thank you all for coming here for the second reading group of the semester, followed by the great Jinan. Appreciate it. So today I'm going to be going over a paper called Interactive Language, Talking to Robots in Real Time. I'm going to be giving you guys a pretty high-level description of what the paper aims to do, and we'll be breaking down some of the components of how they do it. The way that I like to present is pretty interactive, so if you guys have any questions in the middle of the presentation while I'm explaining this stuff, it probably means that I'm not explaining it properly, so just interrupt me and I'll be happy to answer any questions. Great, so first I want to start with the research question. So how can we build a robot that's capable of completing diverse natural language instructions in real time? So this is a pretty open-ended prompt, right? And if you think about this prompt, you'll probably think of something like Siri or, say, Alexa with the screen that is able to talk to you and complete some sort of set of diverse tasks. So people in industry and people in research have been trying to figure this out for a very, very long time, since the 1960s. And it's pretty simple to create something to create a very simple robot that does this. However, when you put some constraints on it, like any other robotics problem, it starts to fall apart. So first, I want to show you guys a very early example of a robot that can respond to natural language prompts. So this was built by MIT, and it mimics a robot table setup with a plunger. So on the top here, the prompt is, will you please stack up both the red blocks in either a green cube or a pyramid? And this robot is able to take a natural language prompt through text and complete that task on a simulated tabletop environment. So this was done in the 1960s, right? This is before any sort of ML. This is before, the perceptron was in the 1960s. This is before most modern techniques in AI. You can see it works on not what I meant to do. Works on a host of different prompts. It's also able to keep a conversation with the user. But this isn't really that impressive, right? This is just a single robot in a simulated tabletop environment. And the author later came out and said in the 90s that he just followed a script for the most part, right? So this is just scripted behavior. So something a little bit more impressive came out in 2022. So this is Palm Seikan. So this is a bit of a better example of a robot that can follow a natural language prompt. Oop. So over here, the robot's given a prompt. I spilled my Coke on the table. How would you throw it away and bring me something to help clean? It's able to analyze this prompt and using a method that I described earlier last semester, it's able to plan long-term, break it down into subtasks, and eventually complete this task. All right, almost there. And it delivers the sponge. It's obviously very impressive, right? So previous research has been able to produce a robot that exists in real life and gives us the ability to converse with it with natural language instructions. However, there's never been a robot that can capably respond to a very large number of diverse commands, right? So Palm Seikan, that robot that I just showed you, that's pretty much the state of the art. PalmSayCan can only break down tasks as long as it can do subtasks. So bringing over a sponge, for instance, or picking up a can. If you tell it to go to the grocery mart, it can't do that. Or nudge the can to the right, it can't do that because it has a very limited vocabulary. We also don't have a robot that can follow interactive commands in the moment. So in the case of PalmSayCan, you give it one command, it plans for an entire long sequence, and it executes that. You can't tell it, hey, you messed up picking up the Coke can, can you go back, right? So that is until now. That's what this paper tries to address, is these three criteria. We take that original research question, can we tell a robot to complete a diverse natural language task in real time? And we impose these three constraints. It exists in the real world, can respond to a large number of diverse commands, and it's interactive in real time. Yep.
So what is that large number? And what was that lower number?
So the lower number is 92 for PalmSayCan. So essentially what they did in PalmSayCan is they had a robot that can do 92 different tasks in the kitchen, right? And then they made a method where you can give it a very long natural language prompt. So for instance, bring me something to clean up this Coke can spill. And it'll say, cool, the first thing I should do is pick up the Coke can, then I find the trash, then I take out the trash can, put it in the trash, so on and so forth, until it completes that. Breaks it down into subtasks, one of those 92 tasks.
So it
And
is essentially taking the instruction, doing NLP on it to obtain the language states, and then parses that into a sequence of string or a sequence of like those one of those 97 tasks. Make a sequence out of that and then execute it.
Yeah, I can tell you a little bit more after this, but essentially what it does is it breaks up a very long task into one of those 92 tasks, and it executes those in sequence. Yep.
You mentioned that if you gave it a task like nudge the cat to the right, it wouldn't be able to do it. Why is that the case?
That's just not in the robot's skill set. So that's not what the authors trained it to do previously. So it had a predefined 92 skill set, right? 92 different skills it could do. Nudging it to the right or doing something completely unrelated to the kitchen, that's not in its skill set. So it can't perform those tasks.
Well, okay. For instance, let's take the task that we did where you spilled the Coke can, right? One of the actions within that task was taking the can and moving it aside, which to a very large extent is just moving the can, nudging it to one side, right? If it is possible for the robot to do that sort of action within that task, why is it not possible? Why is that not generalized to a point where it can do that action on any given task?
So I can go over PalmSayCan a little bit more with you after this, but essentially what it does is it takes that natural language prompt and it one-hot encodes it to 92 different subtasks. So just because nudging it to the right isn't a subtask, it can't do that. Right? It didn't learn that skill. Think about it like it started a policy, it executes that policy all the way through.
I think what he's asking is that if you can't just nudge it a little bit, and just do maybe permutation of nudging it that translates to a very elegant task that is not expected.
Well, also, that's more like what you're saying is more like you can ride a bike but you do not know how to balance. It is a skill. In order to ride a bike, one of the skills that you need to develop is the balancing part, right? So it seems like nudging a can is rudimentary to cleaning up a spill. So shouldn't it be able to do that?
So if you want to think about it like this, is it executes a function, and the only thing the function does, it doesn't understand that it's nudging it right. It's an RL algorithm, or it's an RL policy. All it knows is it sees what's in front of it, and it's supposed to move the can over or pick it up, rather. That's all it knows. It's like a function call. Nick?
I assume that it would be capable of doing like the nudge the can thing, but the problem would come in interpreting what that's supposed to mean for like what it's supposed to do, right? Like it has the ability to like grab it and then move it somewhere else, but just saying nudge the can to the right, I assume that it doesn't interpret that as pick it up, move it. If you were to maybe tell it a different way, then it would be able to do that?
Well, it's not that.
It's not that.
So again, it's like it's like there's a map of 92 different functions, and it just tries to choose the function that best satisfies the natural language prompt at the time. So that's just down to the technical implementations. You can very easily add that as a sub-skill later. And this paper kind of goes over that. It's by the same lab, where you can have a more expansive set of subtasks that let you do pretty much any sort of long-term horizon task. Yep.
One last question.
Yeah.
Can you please go over some of, or like at least at a high level, can you just go over the reason why the implementation restricts the policy from not doing the sub skills by default?
So, sorry, can you say that again? Why doesn't restrict the yeah?
Why does the technical implementation of PalmSig restrict the use of a sub skill, because it knows to do the broad thing, and in the process of doing the broad thing, it does the minor things as well. So why does it not? What part of the technical implementation prevents it from learning that minor skill as well?
So it's not that it's preventing it from learning the minor skill, it's just not in the skill set to begin with, so it can't select that skill. So I don't want to pull up the slides, but the way that PalmSig kind of works is you know prompt engineering, right?
Yeah.
So essentially what it does is it limits what the LLM can output to 92 different actions. And it says, given this question, how can you best clean up a Coke spill? Clean up this Coke spill and bring me a sponge, and so on and so forth. It says, number 1, you can do this, one of the 92 actions. Number 2, you can do this action. 3, this action, so on and so forth. So it's just simply not in the original 92 instructions. Yep.
So I guess, to my understanding, is that the determinism of like the 92 means I can't go for a sub-skill for any of the 92.
So there are 92 sub-skills. So
I guess I mean sub-skill.
Yeah,
Like,
yeah.
I might not go over right, I'm obviously measuring the right, but I can't use that sub-skill because it doesn't map directly. So I can't use nudging because it doesn't map to not over, right? It's just a subsection of it.
Yeah. So let's say that you train an RL algorithm to stay in between the lines while you're driving a car, like Tesla, right? That RL algorithm, if you tell it to turn left, it doesn't know what that is, right? It's just staying between the lines. Just as an example.
But
right?
the thing is that it's two different tasks, right? What I'm trying to say is to do a complex task, like what PalmSig does, you need to master a couple of rudimentary tasks. And what you're saying is that it can do the complex task, but not the rudimentary task, which is why I'm confused.
So I'm not saying that it can't do it, it's just simply not in the skill set. So the LLM can't pick that out of the 92. So we limit the language that the LLM can output to those 92 different tasks. That's all. So I'll go over it with you later. That's all it does. Cool?
Yeah, cool.
Okay. Cool. So until now.
Here's push the green star between the yellow.
You guys can't hear that. So interactive language aims to solve, just to recap, aims to solve this problem of telling a robot to complete diverse tasks with these 3 constraints. 1, the robot has to exist in the real world. 2, it can capably respond to a large number of diverse commands. 3, it can follow interactive commands in the moment during execution. So here's a sample video.
Push the green
and then we'll go,
here's push the green
we'll
star
go over how it
between the
works.
yellow blocks, which has a goal that is compositionally spatially defined. Here's move the blue triangle to the right of the green circle, where the goal is defined as a spatial relation from the robot's camera frame.
Great, so those are just some examples. It'll explain to you the whole paper if we keep watching it, in which case I'm useless. So now let's go over how they're actually able to give diverse instructions to this robot and have it perform tasks in real time. So the first step is getting a crazy amount of data. Second step is imitation learning on the data that you collect. The third step is providing a novel architecture that allows for imitation learning. Right? This hasn't been done before, so we're going to be going over all of these 3 things. So first, the data collection method. So as you saw there, the robot is in a fixed tabletop setting where the robot is constrained to a 2-dimensional plane. Right? So what they did is they had a bunch of teleoperators play with this robot with a bunch of blocks on a table and do a bunch of different long-term horizon tasks. So for instance, they'll tell the teleoperators, hey, arrange these blocks into a smiley face with the green blocks being eyes. And from there, they'll collect all the sub-movements that you need to make in order to arrange these blocks into a smiley face, for instance. And after they collected 3,000 hours of this, they labeled 6,000 episodes in simulation and real-world demonstrations of people doing things like moving the blocks to the corner, moving a block in between two other blocks, so on and so forth. So they did something called hindsight labeling. Does that make sense? Hindsight labeling, where the task the robot should have been given in order to do this task. Sound good? So for instance, if you're moving all the blocks into a smiley face, you need to move one block next to another block, right? So the action that you would tell the robot is move this block next to this block. Yep.
This is just semantics, but isn't all labels like technically hindsight labeling? Because it's after the fact, right?
Suppose so, yeah. You could do it in real time, but
Okay, then
they did this
we
in
call that
hindsight.
real time, but typically,
Hmm?
like things training, that's hindsight. Right?
Well, I think the reason why they call it hindsight relabeling is also because this would have been the task that the robot would have gotten to do this. However, when they're collecting the data, it's just a person pushing around blocks. The robot isn't given a prompt. The human isn't given a prompt outside of some broad, create a smiley face. So what they're doing is when the person is creating a smiley face, that person is also nudging a block. That person is also pushing a block in between other blocks. And data labelers take these small slices of what people are doing inside of the data set and are labeling the instructions in hindsight, what the instruction would have been if a robot were to do this.
So it's almost like it's more verbosity, right? It just tells it what it breaks the task into minor things, and just that's the hindsight label.
Mm-hmm.
Okay.
Exactly. It's very verbose, which is why out of 3,000 hours of human interaction, they got 6,000 labeled episodes. So from that, they got 6,000 labels of videos of robots interacting with their environment, and then a hindsight label, and all the different actions that the robot took in that time period. Yep.
Just curious, what would happen so here they use everyday robots, right?
Yep.
What would happen if you were to use like a different robot with like the same like machine learning architecture?
That's funny. That's actually what I'm going to do for my research. So you can't use the same exact action space
Right.
because the robots just don't work that way.
So do you have to define your own custom mapping of like the 92 labels like the robot, and if so, is that hard coded, or do you try to do that in a smarter way?
Yeah, so unfortunately, that's why I didn't want to mention too much of Palm Saycan. So this one doesn't have 92 actions. I'll explain that a little bit later when we get into the architecture. So what this is doing is you take the video and the image, and you take the natural language prompt, and it outputs what direction to move the pin. So there's no not the pin, the end of the robots. There's no 92 actions for this one. But yeah, in terms of porting this over to a different robot, you'd need to do some sort of inverse kinematics on their robot and then try to figure out a trajectory that your robot can feasibly do. So it collects 5 labels a second, so you should be able to do something with that. Wonderful. And then out of those 6,000 labeled episodes, we get 87,500 unique instructions, right? So like Jinan was talking about, very verbose. Right? Great. And then from all those labels, all those videos, actions, and language prompts, we're able to train an imitation learning network that can then function on its own later. I'm going to go into this a little bit more in depth of what the robot policy is. But the high-level overview is we have all of our video frames, we have the language prompts, and the output is which way the tip of the robot should move in order to accomplish that task. Does that make sense to everyone? Cool. Great. So obviously something like this hasn't really been done before, so they had to come up with a new architecture. This might interest some of you. This is a multimodal transformer based on an architecture based architecture used to train the robot policy. So what they did here is they took ResNet that was fine-tuned on ImageNet. They used Clip, which was already fine-tuned. They used all the embeddings for Clip. They used the features that ResNet extracts. They fed it through 2 transformers, and then it outputs an action. The action is which way to control the robot arm. So this performs really well compared to the previous architecture that was used for a similar problem. They say that there was a previous architecture. I kind of disagree. It wasn't used for the same thing, even though they compare against it. And we'll see that this has really good zero-shot learning as well. So it's able to generalize pretty well to natural language prompts that it wasn't given before. Yep.
Why 2 transformers? Do they do different tasks?
So it looks like 1 transformer is used to link together the Clip embedding and the ResNet features. And then the other one is used to keep track of time in some way. To be honest, I don't understand this architecture too well.
I think
Yeah, sure.
from the graph, what I see happening is that the language attached to vision transformer is basically exactly as you said, it's combining the 2 modalities, and it converts it into what is a single embedding. Then that embedding is for that one individual timestamp, right? They basically just add the positional encoding, and in this case this is temporal, to that particular embedding, and then that's your first type step, which is like I is equal to 0 or something. I cannot read very well. And then we have the time step before that, and before that, before that, and before that, and the transformer runs on all of those, and then just creates a second sequence. And this second sequence is the temporal sequence that's fed into the temporal transformer, and then after that ResNet, and then the final bit, whatever else.
Yeah, and then the ResNet is just to bring that down into the action space. Yep.
Do they tell you how many number of parameters, train of parameters they have in this one?
They do. I didn't put it in the presentation, but it's in the appendix and stuff like that. And they also have,
Like the order of magnitude?
I don't know it off the top of my head, but it's fast enough where you can do inference 5 times a second. So it's pretty fast.
Oh, no, I was just wondering, because like is the number of data good enough to generalize?
Oh, yeah.
There's much more number of parameters than the number of data points, and typically it's the overfits. But I guess it's really good at different tasks, and that is not trained for. I guess it's trained pretty well. But that could. Okay, so what does that even mean?
So
yeah.
if you want me, so they said that if they added the training curve was such that it still could have gotten better if it had more data.
Okay.
Right. So another order of magnitude might have topped it out for the number of parameters that it has, but I just don't know off the top of my head.
I was just going to say, ask a quick question about the temporal transformer.
Mhm.
When I assign attention to different, like, different periods inside the video, is that just so I understand which actions correlate? I guess I'm trying to figure out, like, I assign attention to different sequences of the actual video, right? But what does that mean for the whole picture?
So correct me if I'm wrong, Jen. But it looks like it's taking the encoded value out of the language intensive vision transformer, right? So the combination of the language prompts and the image at that time. And then from there, it's keeping track of what the encoded value is rather than just where we are in the video.
So it assigns like this action is happening with this vision. That's how we associate the as far as like this
So-
sequence of time. This is the language that corresponds to that action, right? That's
Yeah, so this is the language and the photo in this video sequence that corresponds to this action that you should take.
Okay.
Gotcha. You want to add? Yeah.
No, go on. That was perfect. My question is, I have 2 questions actually.
Yeah.
First, what was Clip fine-tuned on?
What was what fine-tuned on?
Clip.
Clip? It was the default clip. And then they fine-tune it on pairs of, they randomly took an image from the trajectories, and then it was the natural language prompts. That was the hindsight label.
So you fine-tuned ResNet but not Clip.
You do fine-tune clip on that. They have more details in the appendix. But yeah, they fine-tune it on, can you see my mouse?
Yeah.
They fine-tune it on these images, so they randomly take a image from the trajectory, and they take the prompt, and then they take the embedder of the clip after they fine-tune it.
I didn't understand, sorry.
Sorry, the encoder of clip after they fine-tune it. So clip assigns labels to images, right? No?
Right,
Yeah. Okay. So clip assigns labels to images. So it takes an image from the trajectory, and then it says this is the caption. It fine-tunes it, and then it takes the encoder part of the language part of clip. So the thing that takes the sentence and encodes it.
After encoding. Okay.
Mm-hmm. And then that's what they feed into this language intensive division transformer. Gotcha.
Second question.
Yep.
How does cross-attention work?
To be honest, no clue in this one. I don't know. I didn't look too much into lava. Cool. We could talk about it after.
Okay.
Yeah.
It's gotta go.
You're good. Wonderful. So after we've trained our model, just as a reminder, the inputs are the image and the natural language prompt, and the output is what action you should take. The inference method is to just talk to the robot and update our inference every 5 hertz, so 5 times a second. So on the right here, you can see the natural language prompt: move the triangle to the top right side of the heart. We can give it that prompt, it'll start doing that, and then we can interrupt it after that 1/5 of a second and give it another prompt, like nudge the green star left a bit. So using these short-term tasks, we can build up to thousands and thousands of long-term tasks. And I'm going to show you guys another video at the end so you can see what a long-term horizon task kind of looks like. Good? Great, so the results of all this after training, it generalizes really well in simulation and to real life. So it has a 93.5 expected average rate of success over 87,000 unique short horizon strings. Basically what that means is you give it 87,000 different types of instructions, and it's able to generalize to new things that are not in the training set. Right? So doing things like pushing the blue triangle to the top left corner, pushing green star toward the center, it's able to learn that just from the hindsight labeling that these annotators did. And in long-term horizon skills, so this is what's really interesting to me, doing things like surrounding the yellow heart with the others. These are a combination of short-term skills, and we get an average of 85% success rate over 100,000 long-term goals. And I believe they tested this automatically, so the confidence intervals are kind of bad. And long-term horizon skills are things like creating high-level shapes out of the different blocks. So arrange these shapes into a star, arrange it into a hexagon, stuff like that. Sorting them by color, not something you can tell the robot to like manipulate a single cube. You have to tell it to manipulate a bunch of different cubes. So that would be a long-term horizon task. And also placing all the blocks in specific locations, right? So it has some sort of understanding of where location is, has some sort of understanding of relative location, among other things. Yep.
This is kind of you may not know the answer to this, but there's only one yellow heart. So when you say, or there's only one heart shape, and it's the yellow one. So when you say surround the yellow heart with the others, there's like no other hearts that would apply there. But if you said like a star or like a circle, do you know what it would, do you think it would understand to surround it with all the other blocks, or would it just be like the specific, like would it recognize the shape and then just kind of put one thing next to it and be like, oh, it's surrounded?
So when they gave the instructions to the labelers, they told them to be as unambiguous as possible. So I think that probably wouldn't happen. And my best guess is it would be a 50-50, you know? Yeah. Yeah?
So how does this extrapolate? So we know that it has at least a 69% chance of working if it is given a given prompt, if it is given
a long-term prompt, yeah.
Any long-term prompt. Yeah. So how does it work? Or like how you said they tested it automatically, or like using automated testing. So what parameters did they actually test? What type of prompts did they actually generate?
I believe what they did is, what type of prompts they use, stuff like high-level shapes, sorting by color, placing all the blocks in specific locations. So they did test this manually, but I think the way that they got this number was through automation, since it was a perfect number, 100,000, and I also saw it in the repo. They didn't mention it specifically in the paper though. And the way that I imagine they did this is they have all the short-term horizons the short-term commands that they expect would yield this big shape, or putting everything in one place and stuff like that. And then they just checked to see if it completed all the short-term tasks.
So how well does it, so within the particular skill set, can I say that it now knows how to surround the particular shape with other shapes? So if I swap out yellow heart with green circle, at least that we know for a fact will work.
So what this means is that humans can collaborate with the robot in real time and correct poor actions done by the robot in real time. So let's say you're trying to rearrange all the blocks around the heart, and you say, place the red star, in this example, place a red star to the right of the heart, and it overshoots. Flings it all the way, let's say it's toward the bottom of the board, and it flings it all the way to the top, right? You can then interrupt it and tell it, bring it back down, and then next place this cube to the top right part of the board, so on and so forth, right? So you're able to interact with the robot in real time in that sense. Does that make sense?
Good. Yeah.
Cool. Great. So going back to interacting everything in real time, when you take away the interactability, this performance degrades from 85% to 25%. Right? So that's a very big difference, right? So the ability for a human to interrupt the machine while it's in operation means that we're able to yield these long-term horizon goals. Whereas if you don't have this interruption, it'll be around 25% success rate. Yep.
In the automated testing, how did they set up the criteria? If it was automated, then how was the real-time interaction possible?
So the difference between open loop and real-time language. So real-time would be, it sees that it overshot, tell it to not overshoot, correct its path. Whereas open loop is planning the entire trajectory beforehand, and you know what tasks you're going to tell it to do. So for instance, going back to here, an open loop would be like, place the yellow heart in the center, put the red star to the right of the yellow heart, put the green star on top, so on and so forth, and then you tell it in sequence. Once one succeeds, you tell it the next step. You decide that beforehand, right? Whereas in real-time language, you're able to interject and correct the behavior. And I could be wrong about the automated, so I'm going to look into that later after I'm done talking, but these are the numbers they got. Cool? Yep.
So can you just go over really quickly, like how would you give a typical real-time feedback to the robot?
So this system updates 5 hertz, right? So every 1/5 of a second, you can interrupt it and tell it a new natural language prompt.
Okay.
So that's how you interact with it. You'd say, going back to this example, let's say you are trying to bring the red star to the right of the yellow heart. It overshoots. Then you could say, nudge the red star back down, so it's next to the yellow heart. That would be the interactability. Or let's say you tell it to place the blue triangle to the top right side of the board.
So human decides that.
Yes, yes. So a human is able to control it with their voice.
So isn't it in a very elongated way of human just basically controlling that specific arm and doing the task of doing itself?
Yeah. So this is the first time that you can interact with the robot in real time with your voice and have it perform a diverse set of instructions. So previously, like let's say with Siri, right? Say with Siri, you tell it any physical task, it can't do that. Actually, that's a bad example. Let's say for Siri, there's just tasks Siri can't do, right? that it can reasonably do. Like let's say open up Spotify and start my music. Let's just say Siri didn't know how to do that. I know it can. Siri isn't programmed, it's not one of their skills to do that, right? And here, every single skill the robot should have, you should be able to elicit with natural language. Does that make sense? So for instance, nudging the block to a specific location, nudging the block in between different blocks.
So in that sequence, can you give an example where, for example, let's say we change the task, we change the AI to Siri, what would Siri be able to do in this specific task?
So, well, Siri can't do, I don't think it's a one-to-one thing, but 1 second.
Well, like any previous, so what's the new thing here? So in the previous best AI, what was it incapable of doing that this AI was capable of doing?
So I think Palm Seikan is probably the best thing to say this is an improvement off of. So Palm Seikan is completely open loop. You decide every single action you're going to take beforehand. So let's say you tell it to grab a knife, and then it starts charging at you. You can't interrupt it with your voice. It's already doing it. You can't stop it, right? And that might be easy to do, right? But that might be easy to program and say once you hear a voice stop. But the whole system isn't interactive, right? It plans all of its tasks, and a human can't correct its trajectory once it's started.
Well, what's the difference between just adding an if statement? If you hear stop and then wait for a different instruction, execute the instruction. What is different from that to this one?
So what this can also do is follow a large range of diverse tasks, right? That's also something that Palm Seikan can't do. So there's no robot that has all three of these criterion, right? So Palm Seikan only has the first one where it exists in the real world, and it can also respond to a good number of natural language instructions. Like I said, there's 92 skills, let's say, or it can break down anything you give it into those 92 skills, but it can't follow new commands in the moment, right? Including commands that it should be able to do. So for instance, nudging the can to the right, it should be able to do that, but it can't come up with those new skills. But because of the way we train this model, it's able to understand the semantics of language and say, cool, if I see an example of putting a green block in between a yellow and a red block, I can swap out what color the block is, and I can generalize to new instructions.
But that seems more like that's just improvement on image recognition and just natural language processing. If you just put those things into Palm, what is it incapable of doing compared to this one?
So Palm on its own can't do that because it's just it's just a natural language transformer, right? What this does is it takes the images of what the environment is, it takes the natural language prompt, and then it outputs an action as well, right? So you can say, Palm should be able to do that. It's not reasoning, but it should know what to do in that scenario, for instance, or ChatGPT. But then how do you take that natural language prompt and turn that into an action? You can't.
So that's the key thing, is that moving from the NLP and image state to an actionable state.
Exactly. So this grounds what you can tell the robot in real life, right? So normally, let's say you tell the robot what's the best way to fly to the airport, and it tells you, take an Uber, et cetera, et cetera. It can't order an Uber for you. It can't do X, Y, and Z. So this, ChatGPT would be garbage in actually bringing you to the airport because it's not grounded in the real world. So this grounds everything you say to it in the real world, and it produces some sort of action that it can do from the prompts that you give it, while also being interactable. Great. Yep.
So if in this situation during the real-time language phase of things, right? You said that if the interaction continues to correct the task or if it's making a mistake. What happens if you, or how does the stack of the structure work? Wherein if I say move the triangle to the top right side of the heart, that's the large task, right? And nudging the star a little bit to the left a little bit is like a short-term task. So if I give it another long-term task and say I want to cancel the first one, basically tell it, I don't know, surround the green circle with all of the other blocks.
Mm-hmm.
That's a big long-term task.
Mm-hmm.
Does it complete, or does it like completely context switch to the long-term task, or is it like a stack where it completes the long-term task and does the original one?
So the way that I understand the paper is updates every 1/5 of a second. Once you give it a new prompt, it switches to that new prompt. What it does, in this Lava architecture, right? It just replaces the texturing that you give it with whatever you say after that 1/5 of a second.
Yeah.
Yep.
Then,
So it doesn't complete the first task.
So if
Yeah.
I give it, so then how is it correction? Would I have to re-give it the original task again, or what?
I'm not understanding your question.
So let's define a long-term task. We need to surround the green circle with all of the other blocks,
Mhm.
right? And let's say it overshoots one.
Yeah.
Okay.
Mhm.
Now I tell it, dude, fix that.
Yeah.
Okay.
Mhm.
Once it fixes that, it's done.
Oh, I see.
The
Yeah,
task
you would
will-
have to give it the original instruction again.
Oh.
Yeah. I mean, I'm sure so I should say that the whole point of this paper is just to provide something that meets these three criterion and then also open sources the data set, right? So if they wanted to make a better user experience, I'm sure Google can figure it out. But this is just
Is it the third thing, or like the third development really not that great, because all it's really doing is just listening for instructions and interrupting them?
You can say that, but it's also
What's the complexity?
so it's following new instructions in inference time, right? While the robot is running, right? And I understand that. I mean, yeah, you could also just make it a stack and then go back to the original
No,
instruction
but-
as well.
So,
Mhm.
my question is this, right? If this understanding new commands that we have made, why can so you can just do that wherever it hears anything, it reacts to that immediately. Instead of it just interrupts the current task and does it immediately. That seems like just a basic logic, right? Why is that a resource development?
So something else that POM-SE can, I didn't want to go too deep into POM-SE can, it's also incredibly slow. And you can interrupt in meta-execution. And again, like you said, you can make it you can program it really easily to be interrupted mid-task, right? But then once it starts a new task, it's very slow. The whole point of this research is, let's say a robot is doing something dangerous, a human can reasonably tell it to stop. It can correct it in real time. That's the new development in this. And that's what it means by interactive commands in the moment. Yeah. Yep.
I guess my one question, in comparison to this, maybe I can understand Julian's question.
Mhm.
You brought up the point where if I just say like, okay, every 5 seconds check to hear if I heard the word stop, and then
Mhm.
that's the case, make it a new command, right?
Mhm.
As far as a purpose, like as far as an action space point of view, if all I'm doing is I check it 5 times every second, because someone say do this instead, right? And I make sure that's my new task. What's the difference between option A and option B? In the sense that there's no when in option B where I have 5 minutes a second, I check for a new task and I switch to that task. It's no different than just starting over with a new task, like in POM-SE. Like obviously it's slow and logistically, right?
Mhm.
I'm sure it would be different, but at like the core level, what's really different between those two things? There's no recollection of the previous task where, for example, say I said, click the yellow heart in the middle and make
Mhm.
sure that the greens are on the left and right of the heart as I build a circle around it, right? And if I said that like, actually shift them like 30 degrees, counter.
Yeah, I think I understand your question.
Yeah,
It's
or
just
like, you know what, I like.
Yes,
like,
yes.
you would-
So-
you would add a little bit of like attention
Mhm.
to like that frame, right? But the
Mhm.
overall like sentence is still very important.
So the difference between those two approaches
Yeah.
also is that so POM-SE can. Okay, how about I answer this afterwards, just because I'm running a lot over time.
Yeah.
I'll just answer it later. Just the difference is two different research goals, right? POM-SE can takes a very long time to do its subtasks, and the whole point is that it's not really supposed to be interactable in real time. These subtasks are not meant to be interactable in real time. This task is better suited for interaction with the robot, kind of guiding the robot with your voice rather than telling the robot to do something and it trying to figure out stuff on its own. We'll talk.
How is that an innovative step
Yeah, I'll answer later. Gotcha. Cool. And then just to wrap this up, there's also the language table dataset. So they open sourced all these 6,000 trajectories with all of the videos, natural language prompts that go along with it, and the action space. And a full simulation is available from their data from both human, sim, and staged experiments. Cool, so I think we already went over this a little bit. This is the first paper that proposes a system exists in the real world and can respond to a large number of diverse commands and can follow new commands in the moment. And they open source a large data set so that other people can expand the field of interactive robotics. Great, so thank you. I would show more videos, but I know Sunny wants to do a presentation as well. I apologize for going over time. Wonderful. So we'll talk afterwards if you have more questions. Thank you. Do you have a presentation? Do you want to put in the slides, or do you want to? Gotcha. It'll be up.
No.
The what? Oh, Nick won't see it. Sorry, Nick. I don't have a camera or anything.